Hey there, have you ever wondered about the odds of something happening not just once, but maybe 2 or 3 times in a row? Well, today we're going to move beyond just a single coin flip. We're going to dive into the really fascinating world of compound probability, where one event follows another.
So let's start with a simple question. What are the odds of getting heads twice in a row? Now this might seem like just a brain teaser, but the logic we're going to use here, it's the exact same logic that's used to figure out medical test results or even forecast the weather. By the end of this, you'll totally have the tools to solve problems just like this one.
All right, so the big jump we're making is from a single event, one action, one outcome, to what we call a compound event, which is just a sequence of two or more things happening. And trust me, this is where it all gets really interesting and honestly a lot more powerful.
Now, as we start looking at multiple events, this one huge question pops up. Do these events actually affect each other? And the answer to that question splits the entire world of probability into two completely different categories.
Think about it like this, right? A coin has no memory. What you get on one toss has absolutely zero effect on the next one. But what if you draw a card from a deck and you don't put it back? Well, now the whole game has changed for the next draw. And that one little distinction is the key to, everything we're talking about today.
And that fundamental difference gives us our two big terms for the day. Independent events, which are kind of like strangers passing in the night, right? They have no effect on each other. And then you have dependent events, where what happened in the past directly changes what can happen in the future.
Here's a great way to picture it. An independent event is like rolling a die. Every single roll is a brand new start. But a dependent event, that's more like grabbing cookies from a cookie jar. Every cookie you take means there are fewer choices left for the next person.
So for these independent events, the math is actually super straightforward. To find the probability of both event A times event B happening, you just multiply their individual probabilities together. It's this really elegant and powerful tool for things that don't have any influence on each other.
But for dependent events, we need a special tool, and that's called conditional probability. See that vertical line in the formula, PA/B? You read that as the probability of A given that B has already happened. This is how we figure out the odds when we already have a little bit of inside information about what went down first.
Okay, that's enough theory. The best way to really get a handle on this stuff is to just see it in action. So let's solve a couple of classic problems, and we'll start with that coin toss question from the very beginning.
Okay, two heads in a row. Let's do it. The first toss obviously has a 1 in 2 chance of being heads. Now, because the second toss is an independent event, remember, the coin doesn't care what happened before, it also has a 1 in 2 chance. So we multiply them. 1/2 times 1/2 gives us 1/4. That's a 25% chance. It's as simple as that.
All right, that was pretty easy. But what about that cookie jar problem? Or, the more classic example, drawing cards from a deck. Let's take a look at what happens when the world actually changes after that first thing happens.
So let's say our goal is to draw 2 aces from a deck, but we're not going to put the first card back. For our first draw, the probability is simple, right? There are 4 aces in a 52-card deck, so that's a 4 in 52 chance. Easy enough.
And this is a perfect example of dependence. Let's assume we actually drew an ace on that first try. The deck has now physically changed. There are only 3 aces left, and there are only 51 total cards left. See what happened? The probability for our second draw has shifted to 3 in 51.
This right here is the absolute heart of a dependent event. The outcome of the second draw is completely tied to, it's dependent on, the outcome of the first. The entire world of possibilities, what we call the sample space, has literally gotten smaller. Okay, let's look at conditional probability from a slightly different angle. Forget about 2 draws for a sec. Imagine one card is drawn, and your friend takes a peek and tells you, hey, it's a red card. That new piece of information is a total game changer. So, how does that affect the odds of the card being a heart? This is the real magic of conditional probability. The information that the card is red lets us completely ignore half of the deck. Suddenly, all the black cards, all the spades and the clubs, they're not part of the problem anymore. We get to narrow our focus a lot. So our new world, our new reality, is just the 26 red cards in the deck. That is all we care about now. We've basically been handed this massive clue that makes the entire problem way simpler. And with this smaller world, the math becomes incredibly easy. Out of those 26 red cards, exactly 13 of them are hearts. So the probability that the card is a heart
Given that we already know it's red, is 13 out of 26, which simplifies perfectly to 1/2.
This might just seem like we're having fun with cards and coins, but these concepts, they are the absolute foundation of how we understand the modern world and how we make really important decisions every single day.
And I mean, this is not just theory. Doctors use this stuff to calculate the probability you have a disease given a positive test result. Weather forecasters use it to predict the chance of rain given today's weather patterns. This whole given logic is even at the heart of AI, allowing it to learn by constantly updating its beliefs about the world based on new information.
Before we finish up, just a few common traps to watch out for. Always remember to update your totals if something isn't replaced. Remember that when you see "and," it means you multiply the probabilities, you don't add them. And probably the most important thing, never ignore that given information. It's a powerful clue that's there to make your life easier.
So to wrap things up, I've got a little challenge for you. Notice that key phrase in there, and it's even. That's your given information. Use that knowledge, narrow down your world, and find the answer. It's such a powerful way to think, not just in math, but in how we learn about everything. Thanks for joining me on this Explain.
All right, let's dive into one of the biggest ideas in math and, well, in life, probability. It's how we put a number on chance itself. I mean, think about it. Every single day, you're faced with questions like these. Is my team gonna win? Do I really need this umbrella? Our lives are just this constant stream of moments where we don't know what's coming next. And, while we can't actually see the future, that would be nice, right? It doesn't mean we're just helpless against all this randomness. We've actually got a way to handle it. But that's the real question, isn't it? Can you take something as wild and unpredictable as chance and just slap a number on it? Can you actually measure uncertainty? Oh, you bet we can. And that number, that measurement of just how likely something is to happen, that's what we call probability. It's basically our mathematical roadmap for navigating a world of chance. So, the starting line for any probability problem is always the same. We have to lay out the entire universe of what could possibly happen. And in the math world, this has a name: the sample space. Look, before you can figure out the odds of one specific thing happening, you've got to know every single possibility that's even on the table. You can't miss a single one. So the formal definition is that the sample space, we usually write it as a capital S, is the set of all possible outcomes. But I love this analogy. Think of it like the complete menu at a restaurant. It lists every single dish you could possibly order. And this becomes super clear when you see it in action. If you toss one coin, the sample space is just heads, tails. Easy. For a standard die, it's the numbers 1 through 6. But check this out. For 2 coins, notice how getting a head then a tail is a totally different outcome from getting a tail then a head. The order matters. You have to list them both. And this right here is exactly why that first step is so critical. This is a key habit for Math Olympiad competitors, because if you get that menu of options wrong right at the start, every single thing you calculate after that is going to be wrong too. Okay, so once we have our whole sample space, that full menu of possibilities, we can finally zoom in on the specific outcome we actually care about. In probability, we just call this an event. And it's really that simple. Are you hoping to roll an even number? That's your event. Are you hoping you get at least one head when you toss 2 coins? That's your event. It's the one dish you actually want to order from the whole menu. The official definition is just as easy. An event is simply a subset of the sample space. It's just you picking one or more items from that complete list of possibilities we just made. So if our sample space is 1, 2, 3, 4, 5, 6, the event, rolling an even number, isn't just a phrase. It's the specific set 2, 4, 6. You see how that works? This process of translating words into a precise little set is a huge part of solving these problems. Okay, we've got our 2 main building blocks: the sample space, which is everything possible, and the event, which is what we want. Now we can finally put them together and do the math. And here it is. For situations where every outcome is equally likely, like a fair coin or a normal die, the formula is just beautiful. It's nothing more than fair counting. You just count up the number of ways your event can happen, and you divide it by the total number of things in your sample space. That's it. Let's walk through one real quick. What's the probability of rolling an even number? Step 1. Our sample space is the 6 faces of the die. Step 2, our event, the even numbers, is the set 2, 4, 6. Step 3, we count. There are 3 outcomes we want and 6 total outcomes. Step 4, we calculate. 3 divided by 6 is 1/2. Simple as that. And this is a really crucial point. Every probability you ever calculate will always be a number somewhere between 0 and 1. If it's 0, it's absolutely impossible. If it's 1, it's a total certainty. And pretty much everything else in life falls somewhere in between. All right, now for a really powerful trick, a shortcut. Sometimes counting what you want is actually the hard way to solve a problem. The pros know it's often way, way easier to just count the opposite. Just imagine you wanted to find the probability of getting at least 1 head in, say, 10 coin tosses. Ugh, counting up every single combination with 1 head, 2 heads, 3, all the way to 10, that's a total nightmare. There has to be a better way, right? And there is. The secret is to flip the problem completely on its head. Instead of counting all the things you do want, you just count the one thing you don't want. This is the whole idea behind complementary events. So, if our event is rolling an even number, its complement is simply not rolling an even number, which is, of course, just rolling an odd number. You see? Together, the event and its complement cover the entire sample space with 0 overlap. This leads us to this golden rule. The probability of an event's complement, its opposite, is just 1 minus the probability of the event itself. So, back to that tricky at least 1 head problem. The complement is getting 0 heads. That's way easier to calculate. You find that probability, subtract it from 1, and you're done. It's a fantastic shortcut. So when you boil it all down, the entire strategy we've talked about today comes down to this powerful little process. You take the words of the problem, you translate them into the precise language of these mathematical sets, and from there, it's really just a simple counting problem. We've built a really solid foundation today using fair coins and fair dice, where everything has an equal shot. But what about a loaded die or a biased coin? What happens when the world isn't so fair? Well, that's the next level of probability, and a great question to think about for next time.